Hey, hello out there. For those of you still watching the videos, today we're going to talk about implicit differentiation. We will use methods for differentiating functions that cannot be written as y equals f of x. So suppose we have the problem y to the fourth plus xy equals x cubed minus x plus 2. How do you take the derivative? Everything that we've done so far has been y equals something. So for example, we've had y equals x squared plus x minus the sign of x. You can find the derivative of each piece of those individually. The problem with this one is you have a y here and you have a y here, and you can't solve for y. Yeah, you can factor y out and you've got y cubed plus x, but you can't solve for that y. And so now we're stuck. What we have to do instead is implicit differentiation. Implicit differentiation now means we can find the derivative of things that aren't necessarily functions. You can find the derivative of a circle or an ellipse or a hyperbola. So you can find the derivative of any curve now. So our steps for doing that are take the derivative of each side of the equation, find the derivative of each y term, which is dy dx, isolate dy dx, and then solve for dy dx in simplest form. So we are going to look at some of these derivatives. Let's start with example 1, differentiate the following. X squared plus y squared equals 1. Do you happen to remember what shape that is? It's a circle. Because it has a radius of 1, sometimes we call it the unit circle. Let me see if I can zoom in here a little bit. Here we go. So we are going to use all previous derivative rules. So the derivative of x squared is 2x. The derivative of y squared is 2y. Here's the new part. When you take the derivative of the y term, you follow it up with dy dx. The derivative of 1 is 0. So 2x plus 2y dy dx is equal to 0. I'm not sure why I just wrote that twice, but I did. So we are going to solve for dy dx. I'm going to subtract 2x on both sides. So 2y dy dx is equal to negative 2x. All right, so 2y dy dx is equal to negative 2x. To solve for dy dx, we divide both sides by 2y. So dy dx is equal to negative 2x over 2y. And then you want to simplify as much as you can. Those 2's will cancel out. So dy dx is equal to negative x over y. That is our derivative. So now if we look at example number 2, we have more terms to work on. So we are going to find the derivative of each term. Y to the fourth, the derivative is 4y cubed dy dx. Now, x, y, those are two things being multiplied. That's a product rule. So this is the first times the derivative of the second plus the second times the derivative of the first. So all of this replaces the xy for your product rule. The derivative of x cubed is 3x squared. The derivative of x is 1, and the derivative of 2 is 0. Now our job is to solve for dy over dx, and I've got 2 of them. I have one here, and I've got one here. So those you want to isolate. So 4y cubed dy dx plus x dy dx. I'm going to subtract this y to the right is 3x squared minus 1 minus y. Then I'm going to factor out dy dx. I've got 4y cubed plus x equals 3x squared minus 1 minus y. Then I'm going to divide. 3x squared minus 1 minus y is 4y cubed plus x. That's your derivative. So implicit differentiation, all of the other derivative rules still apply. You just have to include the dy over dx. Example 3, this one's a fun one. There's a lot going on here. We have a trig function, we have a product rule, we have a quotient rule. So there's a whole bunch. So start with cosine. The derivative of cosine is negative sine xy. This is a chain rule. So now we have to multiply by the derivative of the inside. The derivative of xy is the first times the derivative of the second plus the second times the derivative of the first. Yikes. And then on the second piece, we have a quotient rule. So it's the bottom derivative of the top minus the top. The derivative of the bottom is 1. Don't forget dy dx. All over y squared. There's a whole lot going on there. Now, dy dx, we still have to solve for that. There's one on the left, there's one on the right. What are we going to do? I'm looking at this y squared, and I'm going to multiply both sides by y squared. Get rid of those fractions. So kind of a cross-multiplying thing. So I've got negative sine of xy, x dy dx plus y. And I'm multiplying both sides by y squared equals 2xy minus x squared dy dx. So that takes care of the fraction piece. That's a good start. But again, I still have dy dx here and I have dy dx over here. The problem with the one on the left is it's trapped in that bracket. So the only way to get it out of there is to distribute. So I am going to distribute negative sine of xy and y squared. Distributing was my algebra lesson yesterday. Sine of xy, y cubed. Okay. So I distributed the sine of xy to x dy dx. The sine of xy is glued together. Then I had the y squared that was on the outside, x dy dx. And then that sine of xy again, y squared with y became y cubed. And the right-hand side is going to stay the same. So 2xy minus x squared dy dx. Now that we've gotten rid of the parentheses and the brackets, things are free to move around. So I'm going to keep the dy dx terms on the left and everything else on the right. So negative sine of xy, y squared x dy dx plus x squared dy dx is equal to 2xy plus sine of xy, y cubed. And then 2 more steps. I know this is a long problem. Factor and divide. I'm going to factor out dy dx. Negative sine of xy, y squared x plus x squared is equal to 2xy plus sine of xy, y cubed. And divide by everything that's with the dy dx. So dy dx is 2xy. I'm actually going to move that y cubed to the front. So it doesn't look like it's inside of the sign. Over negative xy squared sine of xy plus x squared. There we go. Kind of crazy, but that's the derivative. Here's our final answer. All right, find the slope of the tangent line e to the xy equals x plus y for the point, or at the point, -1, 1.28. All right, we can do this. So if I have e to the xy equals x plus y, there's actually a couple different ways you can write this. We'll start with the way that it's written. The slope of the tangent line, as a reminder, comes from the derivative. So the derivative of e to the x is e to the x. So this is e to the xy. This is a chain rule. So now I have to multiply by the derivative of the exponent. So it's the first derivative of the second plus the second times the derivative of the first is equal to the derivative of x is 1 and the derivative of y is 1 dy dx. So again, looking for that dy dx, there's one on the right. There's one on the left trapped in the parentheses. So I'm going to distribute e to the xy x dy dx plus e to the xy y is equal to 1 plus dy dx. I'm going to move the dy dx terms to the left. E to the xy x dy dx minus dy dx is equal to 1 minus e to the xy y. Factor out dy dx. E to the xy x minus 1. 1 minus e to the xy y. And divide. Dy dx is equal to 1 minus e to the xy y over e to the xy x minus 1. That's a mouthful. So that's the derivative, but in order to get the slope of the tangent line, we actually have to substitute -1 and 1.28. So dy dx at the point when I've got -1, 1.28 is equal to 1 minus e to the -1, 1.28. 1.28 is my y over e to the -1, 1.28. X is a -1 minus 1. And in my calculator, let's see if I can figure out what this is. When I put all of that into my calculator, I have a -0.56. Now, I feel better when we're in class together and I can reach out and say, hey, who else got a -0.56 to know that I'm on the right track? But that's what I have for the slope. If you got a different number, maybe I had a calculator error along the way, but that's what I've got there. Now, before you leave, I want to show you one other thing that happens with these implicit differentiation problems. I want my answer. I'm going to switch colors here to show you. This is especially important if you start to look up some of your answers and you're like, man, I know I did this right, but it's just not matching. So we had said that dy dx is equal to 1 minus e to the xy y over e xy x minus 1. That's what I had said the derivative was. So with these implicit problems, sometimes you can substitute the original problem back in. For example, e to the xy is equal to x plus y. I can take this derivative and say e to the xy is x plus y, here's a y, down here is an x plus y, here's an x minus 1. So I've got 1 minus xy minus y squared over x squared plus xy minus 1. Now, does one look better than the other from the original version to this one? Without the e's, it might be easier along the way. I'm not really sure. It depends on what you're doing. So just be aware that sometimes the answer that you got might not be a solution that's listed, especially if you're looking up other resources, Khan Academy or other YouTube videos, that sometimes there are other ways to substitute the solutions. So just be aware of that. And I did want to say, if you are out there and you've got questions, I know that I'm a one-way video in these videos, but reach out to me, send me emails. If you need to set up a Zoom time, we can set up a Zoom time. I've met with some students already, especially on those hybrid days. And Mrs. Oakes is in school. I know she opened up her Zoom lessons for you to watch live as well, which is great. But if you have just, 1 or 2 quick questions, reach out to me. We'll set up a Zoom time, definitely. So good luck. Keep it going. I hope you're starting to get the groove of things. It's a fast class. It's a very fast class, but keep at it. Keep at it. You'll be okay.